Okay, today we're going to talk about bounds of sets. And one thing we're going to need to mention, you've seen this probably a little bit before, is sometimes you'll see the epsilon, and epsilon usually indicates a very small number. Now, it doesn't have to be, but usually that's what it is, indicates a very small number. And a lot of times you'll see some proof start with let epsilon be greater than 0, and usually the idea it is just a very small number, and so we're going to be coming across that a little bit. And let me start with some definitions, and we'll start with the definition of an upper bound. And let E be a set of real numbers. Then a number, let's call it M, is said to be an upper bound of E if X is less than M for all X in E. So say you have a number that's bigger than every number in the set, then that's upper bound. So again, we can maybe put that in parentheses, i.e. That's kind of a way just to say it in words. It's an upper bound of the set if it's greater than or equal to every member of the set. And then a lower bound, you can guess, pretty much has the same definition, just things switched around a little bit. Let E be a set of real numbers. And move this up a little bit. And number M is said to be a lower bound of E if excuse me, let me make that could we make that a small m just to distinguish it from the previous one? Let me make that a small m. number, be a small m, is the lower bound of E if m is less than x for all, and I'll use the for all notation just so you get used to it, for all x in E. So once again, something's a lower bound if it's less than or equal to all the members of the set. Simple as that. Yes, ma'am. It could be. It doesn't have to be. It could be. Yes, that's right. Yeah, that's a good question. So same with each of these. Let's note that. In both cases, for the upper bound, and we call that the upper bound, and small m, the lower bound, may or may not be in the set. And of course, if it's in the set, then it's going to be greater than all the members of the set except that one, except that highest one that it is. And that's a good question, because we're going to kind of have some examples that'll kind of involve whether or not something's in the set. And then a set that has both an upper bound and a lower bound is said to be bounded. Again, it has to have both an upper and a lower bound to be considered bounded. And so, again, notice that this boundedness is kind of open. I do some, we're mostly going to be using it theoretically, but let me kind of just mention some things here. Look, so if you have like the set, consider the set G. And notice, let's say minus 100, minus 50, minus 4, and many other numbers. Are lower bounds. So, really anything less than or equal to minus 4 is going to be a lower bound. And for the upper bound, again, you could just pick, whatever you wanted. Obviously, 7, just pick anything bigger, 44, 100, 3 million. Let me put that in so you can tell that's different, 3 million. And many others. are upper bounds. So the definition of a bound really isn't too precise. It's just saying it's just going to be something bigger than or equal to everything in the set. And then now you can see here sometimes the bound is in the set and sometimes not, and sometimes it can't be. So let's say if you have one like this, let's say if we consider this set here. So we'll call this set A, and let me just call it like an interval like this. Let me maybe make it start at, I don't know, maybe 5. Let me start at 5 and go to 10. Now notice that for the lower bounds, might be, 5, -4, -2, and many others. You really anything and any number less than or equal to 5. And the same for the upper bound. You could have, like 10, 12, 15, and many others. I'm just throwing some out there. And actually an infinite number. Now, one thing to note on this problem with Emmy asked before about if it's in the set, notice you can have a lower bound. In this case, you can have a lower bound that's in the set. In this example, that is in the set, namely 5. But here, we have no upper bound. That is in the set. Because 10's not in the set, and anything less than 10 is not going to be an upper bound, huh? Good. Yes, right. The upper bound could be 10. Right. Mainly because, yeah, right, because we're excluded. That's right. And so, and like I said, if you think about it, then there's nothing less than 10 that could be an upper bound, huh? Because if you tried to say 9.99999, you could always go something bigger, 9.99999 with more 9s on it. It would not that would be in the set. So yeah, so if you tried to do and like I said, I think you guys yeah, I'm sure you understand, but let me just mention. So if you tried 9.9999, is an upper bound. But it can't be, because you can always find one bigger, which is still in the set. Just put more, just extend the decimals farther, is in the set and it's bigger. So sometimes your bound can be in the set and sometimes not. And so, of course, obviously, anything less than 5 is not in the set, and anything greater than 10 is not in the set. In this case, even 10 itself is not in the set. Any questions so far? So that leads us to what we call a maximum. And let it be a set. If there is an upper bound M that belongs to the set, we call M a maximum. And so then we write that M equal the max E. And as you can guess, we have something similar for the minimum. Let E be a set of real numbers. If there is a lower bound, once again called small m, that belongs to the set, we call small m a minimum. And we write it as m equals the min the min of E. So if it happened to belong to the set, if there is such a number that's upper bound, so if there's an upper bound M that does belong to the set, we call that a maximum. And if there's a lower bound that belongs to the set, we call that a minimum. And then so so for example, let me take that last one I put up. What was that? A was defined by the interval 5 to 10. And so in this case, again, we have the parentheses here, so 10's not included. So the minimum of A is equal to 5, but A has no max. Now we're gonna have we'll have a name for M or for 10 pretty soon. If you're wondering, okay, where does 10 come in? We have a name for it that we'll get to in a minute. And so now one thing, if you think of this for a minute, note that the reason this didn't have a maximum was because there was no biggest number, right? There was nothing in the set that was the biggest number. And so if you have a finite set, that is bounded, of course. Yeah, it's a finite set. Maybe just say it that way because any finite set's going to be bounded. If you have a finite set, the max and the min will always exist. Because if you have a finite set, it's going to actually have a finite number of elements. If you no matter what you might have, let's say if you're starting, I don't know, let's say at 4, and no matter what you have, 4.2, and maybe just some random numbers, 5, and let's say you have a bunch of ones in between, as long as they're a finite number, and let's say you have 1,000 and maybe 50,000, then let me give this a name. Let me call this set B. Then the min of B is always going to be the smallest number in the set because it's a finite set. So there's always going to be like a smallest one. And the max of B would be like the 50,000. So if you have a finite number of elements, you're always going to have a minimum and a maximum. See, the problem over here, we had an infinite number of points. And again, on the lower one, since our interval included the 5, it was part of the set. But on the upper end, 10 was not a maximum because it was not in the set. Any questions? Any questions on any of that? Mostly sort of definitions for now. So again, we have another name. So again, maxes and mins may or may not exist. They're going to always exist if we have a finite number of elements in the set. Sometimes they'll exist even where I have infinite elements, like it said here. 5 was a minimum, but there was no maximum. And if you have a closed interval, obviously you're going to have a minimum and a maximum, if your endpoints are included in the set. And so we have some things called, sometimes for short, they call these sups and infs. But the actual name is Supremum and Infimum, but sometimes we'll just call it these. So again, we talked a lot about upper bounds and lower bounds. And what's called the least upper bound or the supremum let E be a set of real numbers that is bounded above and is non-empty and suppose M is the smallest of the upper bounds, then we say that M is the supremum or least upper bound of the set E. So again, we have like all the possible upper bounds. The smallest of those is what's called the least upper bound. And that's also called the supremum. So again, let's go back to our last example that we had. We said that we had 5 to 10. And then sometimes, like I said, we will maybe just say soup. Let me write this up here. So up here, we'll say like M is the soup of E for short. A lot of times we say that. So in this case, so for the example from 5 to 10, here, the supremum of the set A is 10 because it's an upper bound and it's the smallest of those upper bounds. Because we said really anything bigger than 10 could also be an upper bound. And so 10's an upper bound and it's the smallest, so it's called the least upper bound. Even though it was not a maximum, remember, maximum was defined as being in an upper bound that was in the set. The supremum may or may not be in the set. And so let's go to the other definition. It's almost exactly the same thing, just the other way. So the other one would be the greatest lower bound. Or in I probably wrote that wrong before. Infimum is the way I think it's infimum. I'm probably gonna write this differently every time. So, but infimum and the greatest low bound the infimum. So let me write it similar way I did before. As you can guess, it's really the same idea. Let E be a set of real numbers. That is bounded below and non-empty. And suppose that small m is the largest of the lower bounds. Then we can say m is called the infimum. Write that a little bit better. Or the greatest lower bound. And then we can say, usually we just, rather than say infimum, we just say m like that. Any questions on any of that? All makes sense to everyone. Move this down. Okay. Let me pick some things here. Let's say we have set 3, 7. So let me write some example down here and see if you can determine what the sup, the max, and the min is, if they exist. So take a look at each of those and take a few minutes, see if you can see what the inf, the sup, the min, and the max are. So for the 3 to 7, what would be the inf? Mhm. And the sup? Mhm. Mhm. And the min? Is there a min in this case? B. And is there a max in this case? 7, huh? Oh, by the way, one thing, of course, to notice, if there is a max for a set, it'll be the same as the sup. And if the min exists, it'll be the same as the inf. And for the next one, inf, obviously 2. Sup is 8. Is there a minimum this time? No, because the greatest lower bound is 2, but it's not in the set, so because not in set, there's nothing in the set. I don't know if I just say none. Then the upper or the maximum obviously is 8, and the next one, you guys probably understand this, minus 12, and the sup is 88, and again the min would be minus 12, max 88. Now on the next one, it really, no inf really exists. Sometimes they might call it minus infinity, but according to our definition, the greatest its lower bound is bounded if it's bounded below. So since it's not bounded below, there's no lower bound. We really don't have an inf. So this would be none. And then obviously the sup is 14, and obviously there's no min. And the maximum doesn't exist either, huh? Because 14 is not in the set. And again, here, the fact we have a union doesn't really affect anything. You still look at the the smallest and the largest. So once again, it's going to be minus 8. and 100. And -8 is in the set, and this is not there. Any questions on any of that? Any questions at all? Now, sometimes, again, like I said, technically, usually you really don't deal with infinity or anything, but sometimes books will give you something like this, just a sort of a more trivia. So if you think of what is the inf and sup of the empty set. Again, this is just sort of more trivia. So here we'll allow infinity to be used. So what would be, does anyone want to guess what the inf, so it's going to be the greatest lower bound. Yes, that's right, it'd be infinity. It seems like that's counterintuitive, huh? The greatest lower bound, because really everything would be a lower bound to the empty set, because anything is smaller than something in the empty set. In other words, say 100 is technically, now once again in our definition we said that we weren't considering sets that weren't empty, so we're usually not going to do with it, but sometimes they'll deal with the empty set. And if you say, okay, if you take 1,000, 1,000's theoretically smaller than everything in the empty set. 1,000,000 is smaller than anything in the empty set. 1,000,000,000,000. So the greatest lower bound is infinity, because no matter, that's as high as you can go. Then, as you can probably guess, the sup then is right, exactly, negative infinity, right? Because everything is bigger than something in the set, because there's nothing in the set. And then so the sup is the least upper bound. It's the smallest of those upper bounds. So again, this is more just trivia, but sometimes you'll see this in books. So I just wanted to mention that. Any questions on anything so far? Okay, let me just mention a couple other things here. And so some things about the infimum. And suppose that M is the infimum of the set E. Then one thing you can say for any, like I say, often epsilon could be a small number for, and let me say any, let me emphasize any, for any epsilon greater than 0. Consider M plus epsilon. So we're taking our infimum and adding any tiny number you want to it. there exists an X in E such that X is smaller than M plus epsilon. So in other words, if you have the infimum, and if you add any tiny bit to that infimum, 0.00001, how many zeros you want to add on, there's always going to be something in the set that's less than that. Now, again, and we think about that for a second, if the set has a maximum, excuse me, if it has a minimum, then one of the elements that would be less than that would be the infimum itself, huh? So, like, for example, if you have, so let me just mention that. So, for example, if you have maybe something, again, maybe like this 12 to 800. Let me just say you have this interval 12 to 800, and so the infimum of this set, let me call this set C. The infimum of C is equal to 12, and for epsilon greater than 0, 12 is in the set, and 12 would be less than 12 plus that epsilon. So in other words, take the infimum, add anything to it, you'll get that. Or maybe even a clearer example would be if you have a finite set, let me call this set D. And again, let's say you have 14, 20, 36. And then here the infimum of D is going to be equal to 14. And then for epsilon greater than 0, say if epsilon, say 0.01, then 14 is in the set D, and 14 is less than 14 plus 0.01. In fact, it's the only number, in that case, it's the only number in the set that would be less than the infimum plus 0.01, huh? So sometimes, in fact, sometimes you'll have to, again, we're going to do it theoretically, but sometimes the only one that'll be in the set that's less than the infimum plus epsilon will be the infimum itself. And other times, of course, if you have a case like this, let's say if let me call this set E, if you're going from 20, the interval, to 40, once again, the infimum of E is going to be 20, and then, let epsilon be greater than 0, then there exists an X in E such that X is going to be less than 20 plus epsilon. Again, usually we don't do these with numbers too much, but this kind of gives you kind of a feel what's going on. Once again, no matter, so now in this case, notice 20 is not that value that could be less than this, but no matter how tiny epsilon is, because this interval goes right up to 20, but doesn't include 20, no matter what epsilon you pick here, there's always going to be something in the set that's less than that infimum plus epsilon. So no matter what you add to the infimum, there's always something in the set which is in fact strictly less than that number than the infimum plus epsilon.